Alright, welcome back. I think the next problem on our handout about related rates problems gets a little spooky. So let's make sure we understand how to set this one up, because it involves some things that you wouldn't have thought of right off the top of your head. As it happens, there were problems like this on the Indiana teacher's exam that I took a couple months back now, and it always kind of makes my chest a little tight when I see these guys again. So in this problem, I hope you've read through it already, but what is happening here is there's a lamp, it's a 5-meter tall lamp, and it's casting a shadow on this guy who's 2 meters tall and he's out some distance away. He is XP meters away from the base of the lamp here. The P, I think, stands for person. Alright, and so he's got a shadow out behind him that is as long as XS. I think that X, it's just the X-axis direction, and S is probably for shadow or something like that. And what the problem is asking us to figure out is, as this guy starts walking towards the lamp, what is the rate of change of the position of the end of the shadow here? And they're calling the position of the end of the shadow just X in the problem here. There is a nice drawing that they provide for you that I just cut and paste and put into the handout for you, okay? Although, it's not quite very good to proportions or whatever. Alright, so we've got a guy, he's standing at some location and walking this way, and he's casting a shadow. As he gets closer and closer to the lamp, you can picture that that shadow is getting shorter, and in fact that the shadow is getting shorter faster than he's walking that way, so that by the time he gets all the way over here, the shadow will be all the way down the size of 0. This problem throws in a curveball that was really unnecessary. It tells you that originally the person was at a location XP equals 10. He was 10 meters away from the base of the lamp, and he was moving at a rate of 5 meters per second toward the lamp. So since that's in this direction, we'll call that negative. He's moving 10, so that, he's headed negative direction down the x-axis here. So dxp, the position of the person with respect to time, is half a meter per second. I don't know why they bothered with all of that, because then they say, after 4 seconds, what's going on? Alright, well, after 4 seconds, if he's moving half a meter per second, and he started at 10 meters out, now he's just 8 meters out. I don't know why they bothered with all that. We still are moving at the same rate. His rate of change of position, dxp, person, dt, is still negative 1/2. I don't know why they threw that little curveball in there. That just sort of seems like it makes the problem messier. Alright, but what they want us to do here is find the rate of change of x with respect to time. Now, this probably could be done using your big trig brains, by thinking about like this angle and stuff like that here, but there's actually an easier way to do it once you see the trick. And the trick is to notice that there are two similar triangles on here, similar in the sense of like geometry. Alright, one triangle is right here, and then there's the bigger triangle. And when we have two triangles that are similar to each other, the ratios of their sides are equal to each other. In other words, like for example, if I compared this tall side of this triangle to this tall side of this triangle, that ratio, the size of the big side, the vertical side of this triangle to the side of the vertical size of this triangle, should be equal to like the length of this side of the triangle divided by the length of this side of the triangle. Right. Now, that's a hard thing to think about, but having visualized this as two similar triangles, we then realized, oh, we had a way to get this x and this xs in here. Now, actually, let's expand that x right here into xp plus xs. Because remember, x is actually the sum of these two things. Alright, so this similar triangles trick is going to be hard to remember. But we'll do another example with that in a few minutes. Alright, so if this is how x, let's see here. We could actually expand this here. This would be xp over xs plus 1. You can see how I did that, right? I just broke that fraction up. Alright. I can pull that 1 over to the other side and make this 3/2 equals xp over xs. Let's see, which way do I want to do it? I'll pull that xs over to the other side. So xp equals 3/2 xs. Alright, so this is how the length of the shadow, xs, is related to xp, how far the guy is away from the lamp. Alright, so we now have a way in which these two measures are related. And so, well, we are given things like the change of xp with respect to time. Let's go ahead and take that derivative. Change in the position of the person with respect to time, we'll just take the derivative of this left-hand side here, is equal to 3/2 times the change in the length of the shadow with respect to time. Oh, let's just pull this 3/2 this over to the other side and make it 2/3 dxp dt equals the change in the length of the shadow with respect to time. All right, we actually are given this number in the problem right here, and this is just a constant. So the length of change of the shadow, we can actually just plug in the numbers here, and we get negative 0.3333 repeating. So this is how the shadow's length is changing with respect to time. But remember, we actually want the distance the tip of the shadow is from the base of the lamp. Well, if x is equal to the distance the person is away plus the length of the shadow, then the change in the length in the distance there with respect to time is just dxp dt plus the derivative of the length of the shadow with respect to time. And now we have all those numbers. This one is given to us in the problem. This one is what we just found. You add those together and you find out that the distance of the end of the shadow is negative 0.8333 meters per second. This end of the shadow here is getting closer to the base of the flagpole, or the lamp pole rather there, at a rate of negative 0.8333 meters per second. That's how fast the end of the shadow is approaching the base of the lamppost as the person walks at it at a rate of about 0.5 meters per second. That's a pretty slick problem. I would definitely say you might have to watch that video again to understand what's going on, or maybe we'll move forward and see how another example of one of those problems where we use similar triangles helps us understand how to compute a related rates problem.